Simulation is a key step in any robot development cycle. Developing approaches for human-robot interaction in contact-rich scenarios is difficult since the human must be incorporated into the system. Furthermore, deployment is often time-consuming and has serious safety concerns. In this work, we present the ROS-PyBullet interface, which is a bridge between ROS and PyBullet for reliable contact modeling. The framework provides a full physics simulation utilizing PyBullet, sensing simulation, several interfaces for human-robot interaction, including haptic devices and easy integration with robot hardware. Our paper describes several use cases, including learning from demonstration and full-body telepresence. We hope that students, researchers, and industry will make use of the framework to facilitate the development of the machine learning and control algorithms. The framework is now open source and is provided with full documentation. Thank you.
Hi everyone, I am Daniel, and in this work we propose ToolFlowNet. How should a robot imitate a trajectory in 3D space? Our proposed method, ToolFlowNet, learns from point cloud data for tool-based manipulation tasks using a novel action representation. Here's the architecture. The input is a segmented point cloud where each point has a position and a class label. The backbone is a segmentation PointNet++ to predict per point tool flow. The last part is a differentiable singular value decomposition layer to compute the action. We collect scooping demonstration from a human moving a Sawyer robot with an attached ladle. We train ToolFlowNet to imitate this behavior and deploy it in physical experiments. Thank you very much.
Hello, everyone. My name is Jikun Kang. Today, I'm honored to introduce our work, Learning Multi-Objective Curricula for Robotic Policy Learning. We started with a problem that can we always solve deep reinforcement learning to do a complex control task? The answer is not likely. Well, basically because of two things. First is sample inefficient. Second is complex task doesn't have training signals in the early training phase. So to solve this issue, we use the idea of curriculum learning, where we have a teacher-student network. The teacher is proposed a problem for student to solve. But instead of doing one curriculum, we want to generate multiple curricula in a unified framework. And to achieve this goal, we switch this curriculum generator to a HyperNet-based HyperNN, which generate parameters for each base RNN, and that is correspond to generate for each curriculum. We evaluate our work in the causal world, and we did compare this to some sawdust methods, and we did very detailed ablation studies to prove that each component is very effective. If you are interested in our work, please feel free to drop by and see our poster. Thank you.
Hi, everyone. So today I'm going to propose our approach on outdoor navigation using sparse rewards. And we are trying to deal with the sparse reward problem using heavy-tailed policy parameterization. We observed that the heavy-tailed policy parameterization can lead to better exploration capabilities and better learning capabilities. So we try to use three navigation scenarios: simple goal reach, obstacle avoidance, and uneven navigation. And we evaluate the heavy-tail policy performance, and we observe that it can perform better than the Gaussian policies. And we deploy our algorithm in the real world with a ClearPass Husky robot, and we observe that our method can be deployed in the real robot scenarios without significant performance degradation. So feel free to check out our poster, and you can see some demo videos as well. Thank you.
Hi, everyone. My name is Yannick, and I'm happy to share our work, Tracklet Mapper. Robustly classifying urban ground infrastructure such as roads and sidewalks is a highly challenging task. It is usually solved by training large-scale semantic segmentation models on human annotated data. However, in this work, we propose a different idea. We propose to use tracklets of other traffic participants as the annotation source. We show that it is possible to train a semantic segmentation model only on automatically generated tracklets instead of human annotations, and show that the performance of models trained in this fashion is similar to models trained in completely human annotated supervised fashion. We also show that it's possible to use such models to generate high fidelity HD semantic ground maps that can also be used for planning. If you're interested in the work, please check out our paper in the poster lobby. Thank you.
Hello, everyone. I'm Junhao from Hong Kong UST. In this work, we would like to propose a grass pose detection pipeline based on detecting the contact pairs from the TSDF volume to estimate the 60 poles and the width of the gripper. And the entire pipeline can achieve closed loop at 7 degrees of freedom grasping with real-time performance. And the key characteristic of this pipeline is the context-based pose representation that can avoid the ambiguity problem of the function mapping from visual observation to gripper poses. And we also make use of the TSDF volume to facilitate the multi-view fusion, the contact point sampling, and the collision checking. And for more detail, welcome to join our poster section. Thank you.
Hi, everyone. My name is Henny Benamor. I'm from Arizona State University, and this work focuses on learning neural network policies for safety critical applications, such as wearable robotic devices. What we want to make sure is to learn neural network policies that are safe for humans to use in human-robot interaction scenarios. The way we do that is through a process called neural network repair. You give us an unsafe neural network with safety specifications, and we, in a global optimization process, turn this neural network into one that is safe for the human to use. We provide options for different types of constraints, for example, global constraints, input-output constraints across multiple frames, as well as conditional constraints for specific scenarios and situations. The overall approach allows us to create neural networks that make sure that any controls that are executed are safe for the human. And we also evaluated this on a prosthesis, a lower leg prosthesis. So if you want to know more about this, please talk to me later on. Thanks.
Hi, everyone. So today I'll be talking about sampling-based MPC. These methods, such as MPPI, generally assume very simple distributions like a Gaussian. This can lead to poor sample efficiency, resulting in task failures at low sample amounts. Even when you have a large number of samples, we can fall into bad local optima, which can, again, lead to failure. So alternatively, we can learn the sampling distribution. However, existing approaches, such as flow MPPI, still use these learned samples to update a Gaussian. This again can result in poor scaling with reduced samples. So our idea is to maintain a simple latent space and learn a transformation, in this case, a normalizing flow, which maps samples to a more complex distribution. We can then perform all MPC operations in the latent space. By performing all updates in the latent space, we can improve performance with many samples over baselines. We can also scale more gracefully with a reduction in the number of samples, while other methods may fail. So if this sounds interesting to you, please come out to our poster on the Level 0 lobby. Thank you.
Hi, my name is Joshua from DLR, and our work is on unsupervised domain adaptation and semantic segmentation. As you can see on the bottom left, if you train on a certain source domain with annotated data, this model performs quite well. But if you shift then to a quite different target domain, the performance deteriorates quite quickly. We cannot bridge this gap via manual annotations, since especially for semantic segmentation, this would mean a lot of effort, and there's an infeasible amount of domains. Hence, we developed a unsupervised domain adaptation framework, which is low in complexity and hence is easy to use, which makes it especially well applicable for real-time or real-world applications. Furthermore, we are focusing on how a domain adaptation can actually facilitate domain generalization, which is, of course, the end goal for each model. So if you're interested in our poster, please visit us in the lobby.
Hi, everyone. I am Kelsey Allen. I am talking today about rigid dynamics. So you might not think it, but rigid body dynamics are actually very difficult to model because anytime two objects come into contact, they instantly exchange an impulse that causes a discontinuity in their dynamics. This is hard to learn not just for neural network models, but also for analytic simulators like Drake, shown here in blue, which is unable to capture the elastic contact of a real world cube being tossed, here shown in blue. So here we looked at whether graph network simulators would be able to capture these kinds of discontinuous contact behaviors and potentially do better than analytic simulators. And they do. They're actually performing better than analytic simulators with system identification for real world data, with as few as only 32 real world trajectories with no pre-training whatsoever. As you can see by the blue line being beneath those black dashed lines for both rotation and position error for held out real cube trajectories. They can handle not just these cubes, but also a variety of other shapes because we use the shape information directly when making predictions about how the objects will move. If you're interested to hear more, come talk to me at the poster session. Thanks.
Hi, I'm Kwang Lee from Google. And so in second, Vincent on the first step talked about that we now have the robotics transformer for low-level skill policies, and we have been using POM for language as a language planner. But the key to ground this language plane to what robot can achieve in the real world is have a good affordance value function. And we have been learning it with sim-to-real multitask RL with this PyQTOP agents. So PyQTOP stands for Predictive Information QTOP, and it's an op policy RL agents. So we found that modeling predictive info. What's going on? Are we starting over? Well, okay. Yeah, I mean, PyQTOP is is it playing? I can't really tell. Okay. Or so I mean, okay, I can keep talking. Like, so what we found is like modeling predictive info gives really good representation for sim-to-real multitask RL at really large scale. And you can see that the success rate with explicit modeling predictive information is 20 is like really a lot better than not. And it transfers really well to on-sync task and the real world. So if you're interested, please come to our poster for details. Thank you.
Hi, my name is Sachin Konan, and today I'm going to be presenting our paper, Contrastive Decision Transformers. Decision transformers were introduced in 2021 by Chen et al., and these take as input a history of return, state, and action tokens to predict the action that achieves the desired return in a given state. Previous work has shown that distancing embeddings corresponding to different tasks improves multitask performance. And in our case, we want to distance state action representations corresponding to different returns. To do this, we can leverage return-based contrastive learning. So we introduced a contrastive decision transformer, or ConDT, which has a transformation layer that separates the state action representations corresponding to their return. We trained that layer using our loss function SimRCRL. We tested ConDT across 3 baselines, GYM, Atari 2600, and the 24 degree of freedom adroit hand grip, and we get return improvements of 10%, 39%, and 20%. We also empirically validate that ConDT separates these representations corresponding to the return, which can be seen in these t-SNE plots. Thanks for listening, and we'd love to see you at poster 461 in room 41.
Hi everyone, my name is Catherine and I'm here today to talk about ROAD, a recursive octree autodecoder for 3D shapes. And this was joint work with my colleagues at TRI. ROAD is a novel implicit representation that can accurately encode scenes and large data sets of complex 3D objects. Previous works either encoded a single entity with high fidelity, or they encoded multiple models, but struggled to reconstruct high frequency detail. What's neat about ROAD is that the models are represented hierarchically, and the same network is actually called recursively to increase the level of detail. And you can see that here in this animation. So we show that a single network can actually encode over 1,000 objects given a latent vector per object. And this results in over 99% compression. And thanks for your time. Hope to see you at the poster.
Hi everyone, my name is Fernando Castañeda, and today I'm going to be talking about how we can use control Lyapunov functions to design good reinforcement learning reward functions. So we use CLFs to encode long horizon behaviors into reward functions, such that we can obtain stabilizing policies even when using very small discount factors. This leads to improved sample efficiency and in an algorithmic agnostic fashion. So our method is algorithm agnostic. And in our example, we show that we get an order of magnitude better sample efficiency. We apply it to do real world fine tuning for several experiments, including a quadrupedal locomotion task, as you can see here. And yeah, this constitutes basically a method to in a principled way, incorporate system-specific structures into the reward without sacrificing for the flexibility of model-free methods. Please come to room 41 if you're interested in this idea. Thank you.
Hello, everyone. My name is Vitalis, and I think everybody's going to agree with me when I say that acquiring robotic manipulation skills such as grasping and placing is easiest in open and unconstrained environments. So in this work, we try to transfer these simple robotic skills to complex environments by finding suitable starting configurations for them. And for this, we're using a heterogeneous graph-based affordance model, which we optimize at inference. And our method is composed of 3 steps, where we first find these configurations, we reach them using a motion planner, and finally execute already acquired skills. So we tested this method in various types of simulated scenes with increasing level of clutter, and also we were able to deploy directly on the real robot. And both in simulated scenes and real world environments, our method retained high performance with increasing level of clutter. And if you want to hear it more, please come to room 41 and talk to us. Thank you.
Hello, everyone. My name is Wenlo. I'm here to present inner monologue, embodied reasoning through planning with language models. Imagine the thought process when a person tries to solve some task. I have to unlock the door. Let me try to pick up the key and put it in the lock. No, wait, it doesn't fit. I'll try another one. That one works. Now I can turn the key. The thought process here involves the best immediate action, involved with feedback, and corresponding corrective actions. We implement this idea on with the language model on the mobile robot platform. The task here is, can you bring me a soda? The language model planner gives the action, find the Coke, pick up the Coke, but we're forcing a grasp failure here intentionally to and the successor casing saying the action was not successful, and the scene descriptor says, I see an orange soda. After a short conversation with human, the language model realized the human wants a lime soda and finally picks up the lime soda, completes the task. For more details, if you want to, or if you want to chat about using language model for robots, feel free to catch me after the session. Yeah, Thank you.
Hi, everyone. I'm Deepak Pathak, presenting on behalf of Xingyu Liu, who could not be here. So suppose you train a policy on one robot, which works very well, and you want to transfer this to a very different robot, like on the left and right. How do you do this? So we approach this problem of robot to robot transfer or human to robot transfer through morphological evolution of the hardware as well as software. So we apply this in the context of human demonstration. So we see a human doing something. Now we transfer this demo to a robot, which looks like human hand. And then we evolve this hardware as well as software over time to a different robot. So you can see in the animation, which might come in a second, where all the fingers as well as the hand slowly morph to different shape over time and can be applied to different robots in here. So slowly this whole demonstration will transfer from that hand robot to this. It is changing morphology as well as software. So in the end, it will transfer to your regular two-fingered gripper from the hand that it began with. So it is easy to train on the hand. And then now you can transfer the hand policy to this two-fingered gripper and apply it on your real robot afterwards. So how do we do this? Come to our poster where I can explain this in more detail. Thank you.
Hi, my name is Yann Labbé, and this is our work on megapose. We address the problem of 6D pose estimation of novel objects, given as input the CAD model of an object that has not been seen during training and a region of interest in an RGB image. The goal is to estimate the 6D pose of the object. We introduce megapose, an approach which relies on free contributions. A scoring network to find the best initial estimate among a set of coarse hypotheses, a network for iterative refinement, where the object shape and coordinate system are implicitly provided as inputs, and a large-scale synthetic training dataset we use to train both networks. We evaluate our approach on hundreds of novel objects and show its performance is competitive with others that require the objects to be known in advance for training. So if you want to know more information about this, come to our poster. It will be in room 040. And thank you.
So hi again, this is work by my student Yifan Zhu, and the focus of this paper is on modularity for language condition policies. We want to train a single policy that can easily be transferred across different robot morphologies and manipulators. We can also efficiently do sim to real transfer using this approach. The trained language condition policies can generalize to a variety of different conditions and situations. Now, what's the special sauce here? It's modularity, but the way we achieve this is through a new regime for supervised attention. So by supervising the attention process, we can create modular components within an end-to-end system. And the cool thing about this is that we can trigger these components at inference time. So we know what the individual component has generated and how the neural network is coming to a conclusion. We can also train additional new tasks. So for example, here we're adding obstacle avoidance as an additional module. The learned policies can also, they're also closed loop, which means a human can sort of mess with the robot and the robot can still respond to all of these perturbations. So if you want to know more about that, please talk to me later on in the session. Thank you so much.
Hi, I'm Ryan Burgert, and I just realized this is the last technical oral of CoRL, so I'll try to make it a good one. This is our presentation, Triton, and it's a photographic sim-to-real algorithm. Triton stands for Texture Recovering Image Translation Network, and as a black box, it will take in simulated images like you see on the left and return photographic images like you see on the right. Now, what makes Triton special is that it's temporally consistent over global timescales. So you can see this animation over here. It was actually trained with a single camera view, but everything can move. You see shadows and reflections. This is actually an unpaired algorithm, so we don't actually have any ground truth. We just take some simulated photos and some real ones, and we dump it in a black box. And these photos actually, the simulation photos actually come from 3D Simulator, and we use them to create simulation images. But the secret sauce of our algorithm comes from our neural textures. We combine those together and we run it through an image translation network with some consistency losses to produce the final output. Come see our poster. It's pretty interesting. Thank you for coming.
That's it for the spotlights. I actually like a lot that we ended with the spotlight with CoRL in the slide. So next thing up is award session at 5:05. Enjoy the spotlights. See you at 5:05.